Our speaker is Cordilleran from Baguio City, Northern Luzon. She is an academician for 17 years, handling various courses in biology. She finished her degree in Bachelor of Science in Biology at the University of the Philippines, Baguio, and Master of Science in Biology at the Benguet State University. Currently, she is pursuing PhD in Botany, major in Systematics at University of the Philippines, Los Baños. She is actively involved in plant biodiversity studies and researches on plant natural products. She also served as the head of the extension unit of the Don Mariano Marcos Memorial State University, spearheading all the extension-related projects of the campus. So let's all welcome Ma'am Karen A. Balada.
Thank you so much, sir, for that very kind introduction. So, a pleasant good afternoon to all of us. For this afternoon, I will be sharing my talk on the role of leaf architecture analysis in delineating taxonomically confusing taxa. So, for the outline of my presentation, first, I will be defining what is meant by leaf architecture analysis and why is there a need for us to do this one. Okay, and I will also be showing to you how it is being done. So how is leaf architecture analysis done? And then for you to be able to appreciate the application of leaf architecture analysis, I will be presenting to you some interesting studies on selected Philippine taxa, specifically the genus Hoya, Dipterocarpus, Terminalia, Cucumis, Musaenda, and three selected species of Anacardiaceae. And hopefully, at the end of my presentation, I would be able to convince you to also start doing leaf architecture analysis. So let's start with what is meant by leaf architecture analysis. So leaf architecture analysis is actually the study of the placement and form of various elements constituting the outward expression of leaf structure, including leaf shape, leaf size, marginal configuration, gland position, and venation patterns. In other words, leaf architecture analysis is simply the study of leaf general lamina characters and the venation patterns. So you just need to study the different characters that you would be able to see from the leaves. So that is what is meant by leaf architecture analysis. Now, why do we need to do leaf architecture analysis? Leaf architecture analysis is important when there is a need to identify and classify plants using vegetative characters. We know that since the time of Linnaeus, the identification and construction of relationships between plants have been based largely on the features of the reproductive organs, and leaf and other vegetative characters are often taken for granted or neglected due to the prevailing view that these characters have high phenotypic plasticity. Well, at some point, this is considered true since we know that the plants in general need to be flexible or they need to adjust in order for them to cope up with their current environmental conditions to ensure their survival. However, in some cases, tropical botanists, like here in the Philippines, also tend to find themselves confronted with the need to identify and classify plants using vegetative characters because many tropical plants flower infrequently and irregularly. And another thing is that in paleobotany, or the study of plant fossils, leaf compressions and impression fossils are the most common macroscopic remains of plants. And studying these fossils can actually provide us an enormous amount of information about the composition and the diversity of past flora. So in other words, there are a lot of instances wherein we need to identify plants, but the problem is that there are no reproductive structures that we can work on to ensure to make sure that we are doing their identification accurately. So at these instances, these are the scenarios or the instances wherein we can make use of leaf architecture analysis so that we would be able to carry out the proper identification and classification of the plants. Furthermore, leaf characters, especially venation patterns, are considered to be genetically fixed. So, in the study of Roth-Nebelsiek in 2001, he was able to show that indeed leaf characters are genetically fixed and that these characteristics can actually be used as a taxonomic tool. Okay. Now, here in our country, here in the Philippines, studies on leaf architecture of the following plant taxa were already reported. Like, for example, in 2004, they already had studied several species of Psychotria. And then there's also this study by Larano and Buot in 2010 on the 40 selected Malvaceae species. We also have, there are also publications on the delineation of Cinnamomum species, Hoya, Musaenda, Shorea, Terminalia, Cucumis, Coffea, Dipterocarpus, Dioscorea, Esculenta, and even ferns, Eupolyploids, and the Diplasium. How is it being done? Basically, leaf architecture analysis is done in three main steps. So the first one is the collection and the preparation of the leaf specimen, followed by the observation and the characterization of the lamina or the blade, and lastly, the observation and characterization of the venation patterns. So for the collection and the preparation of the leaf specimen, usually we follow the rules, the standard protocol or the rules that is being used in the collection of herbarium specimens. So first and foremost, before you go and collect plants from the, especially from the wild, you need to process the necessary permits. Okay, that needs to be done first. And then in preparing your leaf specimen, we follow the standard procedure in herbarium specimen preparation. So we press the specimen, we process them, and then we dry them. Okay, so after you have collected and prepared your leaf specimen, you're now ready for the second and the third step, and that is the observation and characterization of the lamina or the blade, and the characterization of the venation patterns. Now, for these two steps, we need to use the manual of leaf architecture because just like describing plants, there are standard terms that are used to describe the different character states of your specimen. Now, this manual on leaf architecture actually was it was pioneered by Hickey in 1973, and then eventually there are series of revisions that were made. And this one by Ellis and the group, this is the more recent one. This was published in 2009. But there is also another 1999 version of this manual that was also published by the Leaf Architecture Working Group. Okay, so these are some of the available manuals. They are you can download them from the internet. Okay, so let's go back. Once you already yeah. Before I'll proceed into the step 2, I would just like to give you a short glimpse on what is in the manual. So first you have there the general leaf definition. So this manual is very helpful because all the necessary descriptions and illustrations are all there. So it includes information about the general leaf definitions, leaf characters, general vein definitions, and then determining vein order, vein characters, and even the leaf margin and teeth, if there are any. In the appendices, it contains outline of characters and character states. And if I recall it right, this particular manual actually described about 54 characters. And then you also have there some examples of fully described leaves, vouchers, and the instruction for clearing leaves. Clearing leaves because there are certain instances wherein the specimen you are working on, you need to clear it out. You need to remove the pigments so that you would be able to clearly see the pattern of the veins or the vascular tissues. Okay, so for this part, I would just like to share to you some examples of blade characters or the general blade or lamina characters that are usually described. So you have their laminar shape, laminar size, blade class, length to width ratio, laminar symmetry, and of course the leaf apex. So let's start with the laminar shape. For the laminar shape, there again, as I did mention earlier, there are standard terminologies that are used to describe this one, and there are corresponding descriptions accompanied by these different shape categories. So for the laminar shape, in my specimen that is presented in this slide, there are three leaves there. So the leftmost is described to be elliptic because the widest area is located somewhere at the middle of the leaf. And then the two other leaves present on the right side of your screen are described to be lanceolate because the broadest or the widest portion of the leaf width is located somewhere on the upper two-fifth of the leaf. Okay, so in this specimen, they are described to be elliptic and lanceolate. And then another character is the laminar area. So laminar area, all you need to do is, well, you need to get the area or the size of the lamina. So all you need to do is to use the equation, you multiply the width and the length of the leaf by 0.75, okay? And you're going to get a value that is in square millimeters, okay? Now, in my specimen here, I already did some initial computations on this, and you can see it there that their value ranges from 10,807 millimeters squared. The middle leaf is 5,983 millimeters squared, and the rightmost rather is 7,910 millimeters squared. Now, using this laminar area, you can now determine the blade class of your specimen. So there is actually a table that was developed by Webb in 1959, wherein there's a certain range of the laminar area that is assigned to a particular blade class. So in my specimen, since the laminar area of the specimen all ranges are all within 4,500 to 18,225 millimeters squared, all these three specimen are classified to be mesophyll. The other one, the smallest category or blade class are leptophyll, and then followed by nanophyll, microphyll, notophyll, and then you have there your mesophyll. The bigger ones are macrophyll, and the largest ones are actually megaphyll. Okay, so those are the different blade classes. Then we also have the length width ratio. So the length width ratio, this is simply the ratio of the laminar length to maximum width perpendicular to the mid-vein axis. So mid-vein axis, that is the major vein that you can see there at the middle of the leaf. So my preliminary measurements in my specimen in these three kinds of leaves, I was able to get the values there of the length to width ratio. So 3.62 is to 1, 3.93 is to 1, and then 3.14 is to 1. So this simply shows that my leaves are quite long. They're in terms of the ratio between the width and the length, my leaves are long. Okay. And then next you have the laminar symmetry. So laminar symmetry, on the other hand, this is simply the width ratio in the middle of the leaf. So all you need to do is to take a look at the width from the mid vein to the left, and then another measurement from the mid vein to the right. And if the values are almost the same, they are considered to be symmetrical. So if the width ratio is greater than 0.9, that is symmetrical. And well, if one part of the leaf is broader, the other one is narrower, then we consider it to be asymmetrical. So in my specimen, all of them are actually symmetrical. And then the next character is the leaf apex. Okay, so leaf apex, we're talking about the shape of the tip part of the leaf, the more proximal part of the leaf. And the leaf apex can be in terms of, there are several ways by which we can describe the leaf apex. In my specimen, well, the leaf apex is actually quite associated with the leaf angle. So in my specimens again, they are described to be acute, broadly acute, and obtuse. So they are quite related to the leaf angle. Okay. Uh, well, here in this next slide, the measurements of the leaf apex angles are given. So this actually corresponds to the leaf shape that was given earlier. And then the next blade character is the leaf base. So if you are describing the leaf apex, of course, you need also to describe the leaf base. The leaf base, again, you just need to take a look at um, the proximal part or the lower 25% of the lamina or the blade, and there are several categories that you can put it here. And in my specimen, as I already had placed there, my specimen are all acute because again it's associated with the uh, acute. Okay. They are all associated with the leaf base angle. Okay, so sometimes if there is no particular curving, there are also other terms that you can use there, like for example, straight. Ibig sabihin, or it means that the angle, or but rather the leaf base does not show any curvature, so straight. And then the angle is less than 90 degrees, which is why they are considered to be acute. Okay, and then of course, oh yeah, this one is the actual measurement of the leaf base angle. So as you can see it there, they all correspond to the description or the kind of leaf base that is observed in this plant specimen, which is actually acute. They are all less than 90 degrees. And then you also have there the leaf margin. So leaf margin basically is the feature of the edge of the lamina. And you have there certain terminologies that can describe the leaf margin. But in my specimens presented here, all of them are smooth or entire because the leaf margins are simply, they do not have tooth. They are not untoothed, or they do not have teeth. In some specimens, they have teeth, and in some specimens, they have even special margin features. Okay, now we're done with the characterizing the leaf blade. Now we proceed with the fine leaf architecture or the venation patterns. Okay, so or the venation characters. So first we start with the primary vein category or the venation type. So you have there in the illustration what is meant by the primary vein. So it is pointed there with the number 1. So that is the primary vein. Primary vein, basically this one is the main vein that you see, the major vein that you find on the leaf blade. Now, there are several categories or venation type. If there is only one main vein, we call it pinnate, as you can see there in the illustration. So it is pinnate because there's only one major vein. However, if there are more, it will be described to be as a palmate. Okay, so palmate, and then there are even other subtypes or subcategories under the palmate category. So, but for this specimen, it is pinnate because there's only one mid vein, okay, that you can see in the specimen. Next is the primary vein size. Okay, so for the primary vein size, you have to measure, this is the ratio of the vein width to leaf width multiplied it by 100. So this I did the measurement in terms of millimeter. So the vein width is something like 1 millimeter, and the length the length width, the leaf width is about 60 millimeters. So I divide that value and multiplied it by 100. I get a value that is equivalent to 1.7. And then from this primary vein size, I will be able to determine now the primary vein size category. So again, there is the ranges that was proposed by Hickey in 1973, wherein if the primary vein size is less than 1.25, it is considered to be weak or classified as categorized as weak. Whereas if the computed primary vein size ranges from 1.25 to 2, which is in this case the 1.7 value that I got there in this specimen, falls under this category, and this will be described to be or classified to be moderate. Those with vein size ranging from 2 to 4% would be stout, and those greater than 4 are considered massive. Okay, so those are the primary vein size categories. So as I did mention earlier, in my specimen, the primary vein size category is moderate. Okay, and then next we have the secondary vein category or the venation type. So we just need to observe, okay, the secondary veins, these are actually the veins, the next major vein that originates from the primary vein. Okay, so you have there in the illustration, the secondary veins or simply secondaries. And the secondary vein venation, there are several what you call this terms that can describe this one. But for this specimen, it is described to be a brachydodromus. Okay, brachydodromus meaning the secondary veins, or simply called secondaries, joined together in a series of prominent arches. Okay, so as you can see it there in the specimen. So the secondary vein category or the venation type of my specimen here is brachydodromus. There are other terms, like for example, claspidodromus, semiclaspidodromus, festooned semiclaspidodromus, and so on. Don't worry, all this the description of these characters and at the same time the illustrations are all there in the manual. Okay, the next fine leaf character is the secondary vein spacing. So secondary vein spacing, all you need to do is to take a look at the spaces between the secondary veins. Do they exhibit proportional, do they proportionally decrease distally or proximally? So in that case, as in the case of this one, it is considered to be regular. Or if the spacing varies over the entire lamina, it is considered to be irregular, and so on. Okay, so for my specimen, there is a proportional decrease distally and proximally. Therefore, the secondary vein spacing of my specimen here is described to be regular. Okay, next is the secondary vein angle category. Okay, so the angle is usually measured, oops, pardon my line there. It's the angle between the secondary vein to the primary vein. And this actually is being measured. Now, if the secondary vein angle is the difference all throughout the leaf is something like within 10 degrees from the base, it is considered to be uniform, as in the case of this one. So as you can see, that the change in the angle from the distal to the proximal part of the leaf is quite minimal, less than 10 degrees. 10 degrees. Therefore, it is considered uniform. The other uh, classification of secondary vein angle category includes inconsistent, smoothly increasing proximally, smoothly decreasing proximally, and so on. Okay, next, tertiary vein angle category. So we're done with the primary vein, we're done with the secondary vein, and then now we're down to the tertiary vein angle category. So if the secondaries or the secondary vein are veins that that are connected or originates from the primary vein, and therefore it also follows that the tertiary veins originate from the secondary vein. So as you can see there in the illustration, the number 3 there. So you have there the primary vein, and then in the magnified part of the leaf there, you have a close-up of the secondary vein, and of course the tertiary vein. So tertiary vein category pattern, you just try to take a look. Do these veins like form a straight connection between secondaries, or do they form an alternating pattern? Okay, so if they form straight connections, they are described to be per current, or if they are okay, they can be considered as per current. But anyways, in the before we go into that category, first we try to take a look first at the um, tertiary vein category. So in this particular illustration, the 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 tertiary vein angle is quite obtuse, okay, because again, your basis of measuring the tertiary vein angle is the angle of the tertiary vein pointing towards the basal part of the leaf relative to the primary vein. Okay, so in my specimen, the measured angle is somewhere between 1.29.6 degrees, which is equivalent to an obtuse category. Okay, so obtuse more than uh, it's more than 90 degrees. Okay, and then for the tertiary vein category pattern, so we're going to take a look at the pattern. This is what I had been mentioning earlier. Does the tertiary vein form a continuous connection between two secondary veins, or does it form alternating patterns? So in this particular case, if it forms purely straight connections, this is referred to now as per current, and or rather opposite per current. Opposite per current, um, the majority of the tertiaries cross between adjacent secondaries in parallel path without branching. So they can be straight, they can be convex, they can be sinuous, or they can be forming a chevron. And so there are different features on this one. But for my specimen, this is considered to be a mixed per current. Mixed per current because the tertiaries both have opposite and alternate per current courses. Okay. Next, we have the quaternary vein category. So if the secondary veins originate from the primary veins and the tertiary veins originate from the secondary veins, it simply follows that the quaternary veins originates from the tertiary veins, as you can see it there in my illustration. So for the quaternary vein category, um, again, this is quite similar in terms of the different the descriptions or the character states of this one is quite similar to that of the tertiary vein category in terms of pattern. So again, does it form as continuous or does it form alternate? Okay, so in this specimen, it's also a mixed per current, meaning quaternaries are alternate and opposite in equal proportion. Okay, and then you also have marginal ultimate venation. So the marginal ultimate venation that is located, of course, at the margin, as you can see it there in the yellow box. And for my specimen, it is looped because the marginal ultimate vein recurves to form loops, and at the same time, it doesn't have any teeth. So there are no teeth. And then lastly, you have the areole development. Areole development. Areole, these are actually the smallest areas of the leaf tissue that are completely surrounded by the veins. So you have it there in the distinct regions there. Taken together, they form a contiguous field of polygons over most of the area of the lamina. So for the areole development, there are several categories. Like for example, do you see any areoles in the specimen? So for this specimen, yes, there are areoles, so they're present. Now you have to distinguish if the areoles are poorly developed, moderate developed, good developed, or paxillate. So again, based on the descriptions that are present in the manual. And in this specimen, the areole is quite good, exhibited good development because the areoles are relatively consistent in size and shape and generally with about 3 to 6 sites. Okay. Okay, so I think that's the last one. There are other characters, fine leaf characters that you can find that you can use to describe your specimen. However, in my presentation, I only screened or enumerated some of them because the others are not actually observed in my specimen, so I did not include them anymore. Okay, so you can actually screen. You do not have to use all the characters that are listed in the manual. Okay, now for you to better appreciate the the leaf architecture analysis, I would like to present to you some interesting leaf architecture analysis studies on selected Philippine taxa. So as I did mention earlier, so you have the Hoya, Dipterocarpus, Terminalia, Cucumis, Musaenda, and selected Anacardiaceae species. So let's start with, of course, the Hoya. So for the Hoya, those who are not so familiar with this plant, Hoya species are actually cultivated and propagated, especially in Western countries, as an ornamental plant. And here in the Philippines, we have a lot of endemic species of Hoya. They are commonly cultivated. Hoya is geographically distributed to the Indo-Malaysian, Australian, Western Pacific region. And among all of these countries, Philippines actually harbors the most diverse Hoya species. In 2018, the COS Digital Flora reported around 119 Hoya species, uh, recorded species here in the Philippines, and just less than 4 years, so this is already 2022, they already had recorded 202 species. So in the last less than 4 years, or almost 4 years, 93 new endemic species were recorded. So if you are not so familiar with the identification or the characteristics of these plants, and you tend to encounter them, however, you are not sure uh, as to their proper identity because it doesn't have any reproductive structures yet, you can actually make use of leaf architecture analysis results, okay, to identify this plant. So the first study was conducted in 2017, okay, by Torrefiel and Buot on Hoya carangdangiana, Hoya bicolensis, and Hoya camphorifolia. So as you can see in this illustration, these three species of Hoya without their reproductive structures look very similar. Okay, so it is not possible that there would be some issues or confusions in their identification. So this is the time where the results of leaf architecture analysis can actually very useful. So when they did actually the leaf architecture of the species, these are their results. So the leaf architectural characters delineating the three Hoya species. So they are delineated in terms of their length to width ratio, blade shape, for in Hoya carangdangiana is more an ovate to lanceolate. Hoya bicolensis is elliptic to obovate, and the Hoya camphorifolia is elliptic to ovate. So other leaf architecture characters that delineates these three species includes the blade class. Okay, so they also differ. Microphyll to notophyll. Base shape, they also differ in terms of their base shape, in their apex shape, secondary vein category, and tertiary vein category, tertiary vein course, and even areolation. Okay, and you can actually make use of these characteristics for you to be able to identify which is which. Okay, which among these confusing groups of Hoya is which of them is proper? They should be properly identified. Okay, another study, again on Hoya, this time Hoya incresata and Hoya crassicaulis. As you can see it there, again, the vegetative structure of these two plants looks very similar. Okay, but then again, if we're going to do leaf architecture analysis, you can see that there are differences, as shown, of course, in their results. So the leaf architecture characters delineating the two Hoya species, Hoya incresata and the Hoya crassicaulis, is the length to width ratio, blade class, leaf form, leaf base, angle of divergence, and areole development. See? Okay, another study on Hoya, this one, this time involving Hoya coriacea, halconensis, and buotii. So these three particular species are again quite similar in terms of their vegetative features. So leaf architecture analysis, they were able to get this result. So you can delineate these three species using their leaf margin, length to width ratio, leaf base, leaf form, blade class, primary vein size, variation of angle of divergence, and again, of course, areole development. Okay, another group or another genera is the Dipterocarpus under family Dipterocarpaceae. Dipterocarpus is regarded as an ecologically and economically important group of timber trees in lowland rainforests in the Philippines. And that we have 10 species in in the country. So you have actually here Dipterocarpus, the apitong, if you're familiar with the tree. And it's a very good timber tree. This Dipterocarpus species are generally indigenous with one endemic to the Philippines. And unfortunately, the majority of our Dipterocarpus species are already considered threatened, okay, under the DAO 2017. Okay, so in this study conducted by Hernandez and company, in 2020, they did the leaf architecture and petiole anatomy of Philippine Dipterocarpus species. And they collected this one from Mount Makiling. Okay, they collected this one from Mount Makiling. And the different, they wanted to know if you can delineate or properly identify this species because proper identification is very important, especially when you're doing conservation efforts. Okay, so the 8 Dipterocarpus species that they use in their study are the Dipterocarpus alatus, D. gracilis, D. grandiflorus, Hasseltii, Kerii, Cancelleri, Philippinensis, and of course, you have the Dipterocarpus validus. And the result, I tried to summarize it into a table so you can actually, they have features that are quite similar, but they can be distinguished in terms of their laminar ratio, leaf base, leaf apex, leaf margin, secondary marginal veins, and of course their areole development. Okay, these are some of the pictures showing the leaf apex of the different species that were studied. Okay, you also have here the different leaf margin. The majority of them are actually quite entire. And in terms of areolation, okay, you have it there for what some of them exhibited the well-developed areolation, and then the others are quite vacillate. As I did mention earlier, when you're talking about well-developed areolation, meaning there is the formation of clear polygons. Okay, and then another morphologic feature is actually the trichomes that are observed among these different species of Dipterocarpus. Okay. Yes, this is actually one way you can actually process your data into dendrograms such as this one, and you can clearly see the relationship of these different species based on their leaf architecture characters. So among them, the first one to separate is the Dipterocarpus grandiflorus, and then you can see that Dipterocarpus kerii and gracilis are quite more closely related, and then there is this observed clustering among them here. Okay. Okay, the next group is the Terminalia. Terminalia, under family Combretaceae, Terminalia, this is actually a genus of mostly medium or large trees. And this includes actually our talisay. Okay, so Terminalia siya. About 250 species are distributed mainly in southern Asia, Himalayas, Madagascar, Australia, and the tropical and subtropical regions of Africa. Many species are used widely in many traditional medicinal systems. Here in the Philippines, Terminalia is the talisay is actually a very good shade tree. Okay. a very good shade tree. So this particular paper by Baroga and Buot discusses the question whether leaf architecture features are useful for differentiating some species of the genus Terminalia, and they actually made use of 10 different species of Terminalia. And they can be result of their blade of their leaf architecture analysis in terms of the blade characters are presented here. So you have their leaf attachment, PTO features, blade class, laminar shape, laminar length to width ratio, base shape, apex shape, and margin type. Okay. In terms of their venation patterns or the fine leaf architecture, okay, I apologize. Medyo maliliit po sila dito. The font are quite small, but you have it there in their paper. Okay, so the leaf architecture characters of that the fine leaf architecture characters or the venation patterns of the 10 Terminalia species. Now, what is good about this one is that you can actually translate your other than translating your data into a dendrogram so that you would be able to see the relationship between these different species of the plants that you're working on. You can also translate your outputs into a dichotomous key. Okay, but this time, of course, the characters that you are mentioning here, the character states rather that you are mentioning here, are more of the leaf architecture characters. So again, this would help a lot in the proper identification of of plants that are quite taxonomically confusing without their reproductive structures. Okay, so you have here examples of dichotomous key. And then another group is the Cucumis. This is under family Cucurbitaceae. Genus Cucumis is said to be one of the economically most important genera of the flowering plants. This actually includes our cucumber, cantaloupe, melons. Okay, so they're all under the Cucumis. Now, in a study by Masungsong, okay, and company, many species and varieties of cucumis have emerged and are being cultivated all over the world because, as I did mention earlier, of their economic importance. And regardless of the several attempts of the early and recent studies to separate the wild species of cucumis from the cultivated ones, there's still taxonomic confusion brought about by the similarities in the morphology of the genus. So their study basically aims to delineate selected cucumis accessions based on leaf architecture. Okay, so these are their results. So they were able to uh, characterize the different cucumis. So cucumis melo, Myriocarpus, cucumis anguria, variety longaculeatus, and cucumis metuliferus. And these are the different character patterns that they were able to generate in terms of blade class, laminar symmetry, laminar shape, length to width ratio, apex angle, apex shape, base angle, base shape, margin, tooth apex, tooth shape up to lobation. In terms of the vein characteristics, you have it here. So there you have here the results from the primary vein, secondary vein, tertiary vein, quaternary vein, up to the areole development. So again, making use of these different characters, you can it will help a lot in delineating the different species of cucumis. Okay, so these are some of the vein characters and patterns observed from the 5 cucumis species that they studied in this paper. Okay, another group is the Musaenda. Okay. Another genus is the Musaenda. So this actually belongs to family Rubiaceae, and there are about 20 species present here in the Philippines. And as you can see it there in the illustration, frequently this genus, the species in this genus are frequently cultivated as ornamentals. And other than that, Musaenda has been reported to have medicinal properties and at the same time having bioactive components with medicinal or pesticidal properties. So in the study conducted in the study conducted by um, Padihea and Buot on the leaf architecture of two species and 9 infraspecific taxa of the Philippine Musaenda and conservation concerns, they made use of two species and 9 infraspecific taxa of Musaenda. So you have there the Doña Luz, Doña Mutia, Doña Alicia, Queen Sirikit, Doña Aurora, Musaenda Felipica, Doña Evangelina, Doña Imelda, Musaenda Flava, Gloria Macapagal Arroyo, and Paraluman. So the leaf blade characters of this selected species and infraspecific taxa are presented here. So they are characterized in terms of their blade class, laminar size, laminar shape, blade symmetry, base angle, and base shape. Also, you have here the fine leaf characters in terms of their um, vein patterns. So again, using this one, it will help a lot in characterizing the different musaenda in the absence of reproductive structures. So for this publication, they were able to translate their results into a dichotomous key so that you'll be able to identify the different musaenda that are presented in this study. And then lastly, I would like to share to you another study on selected Anacardiaceae species. So this is actually this is my my this is my output, and I hadn't published it yet, but I would like also to share it here. So we already know that there are several species in Anacardiaceae that are economically important fruit and nut crops. And this actually includes mango or the Mangifera indica. So in this particular study, I compared Mangifera indica, Buchanania arborescens, and Semicarpus cuneiformis, and these three are usually these three are considered taxonomically confusing, especially when you are on field or even in observing press specimen or barium specimens of these three. So these are the picture of the three specimen, Buchanania arborescens. The lower left is the Mangifera indica, and the right picture is the Semicarpus cuneiformis. Okay, so these are the leaf morphology of the three. So if we are to put them side by side, we can see some of the differences. Okay, so in terms of the gross leaf characters of the three selected Anacardiaceae species, BA stands for the Buchanania arborescens, the MI is for the Mangifera indica, and the SC is the Semicarpus cuneiformis. And they differ in terms of their average leaf length, in terms of their laminar size. Though in terms of blade class, all of these three are are categorized to be mesophyll. They also slightly differ in their length to width ratio. There's also a bit difference in the laminar shape. All of them are symmetrical in terms of laminar symmetry, and there's a slight difference in terms of their base shape. So from acute cuneate to acute narrow concave to acute. And then average base angle, again, there's a difference. Mangifera indica has the widest, whereas the leaf apex, it ranges from broadly acute to acute and obtuse. Okay, but in terms of leaf margin, they're all entire. Now, for their fine leaf characters or divination patterns, again, you can have it there. and some of the font are quite small. But I would just like to show you the dichotomous key that was generated from this three selected Anacardiaceae species. So the Mangifera indica can easily be delineated from the other two in terms of their leaf shape, that is lanceolate to elliptical, a narrow concave acute leaf base, acute and slightly acuminate apex. And then you can distinguish Buchanania arborescens and Semicarpus cuneiformis in terms of their primary vein. So Buchanania arborescens is quite stout, and it's a bit moderate only in Semicarpus cuneiformis. And also in terms of their secondary vein pattern, Buchanania arborescens is Craspedodromus, and then Semicarpus is Eucamptododromus, and so on. And we can actually translate this data into a dendrogram. Okay, so as you can see it there, in terms of relationship based on leaf characters, we can say that the SC or the Semicarpus cuneiformis and Buchanania arborescens are more related or closely related, or they have more similar um, character states as compared to the Mangifera indica. So in conclusion, all of these results of these studies actually had shown that leaf architecture can be very relevant in solving the identity of taxonomically confusing taxa in the absence of reproductive structures. And specifically, these studies pointed out the fact that leaf architecture patterns are very relevant in species identification and description or even delineation, in addressing nomenclatural issues, and of course, confirming the classification or grouping of certain taxa. So these are some of my the references that I use in my presentation. Thank you very much for listening.